We hope you have seen the video understanding number for doctors which we have posted at the link given here. Now we will try to detail to you why randomization, why random selection, why random allocation to treatment groups, and what is the importance of sample size and how to calculate it. Well, here is the whole population, and we cannot do the measurement on the whole population. Therefore, we decide to take a sample of this whole population. This involves two things: the technique of sampling and the sample size. The technique of sampling, if we have done a random selection over a sufficient sample size, it will make probabilities of selection into the study population of all types A, B, C, and D, big A, B, C, and D, equal to each other. So small a upon big A will become equal to small b upon big B, will be equal to small c over big C, will be equal to small d over big D, and all these probabilities will be equal to the sample size divided by the total numbers in the universe, n upon n. And when this happens, then the statistic which is obtained from the small a, b, c, and d will approximate the actual results in the source of population, which is obtained from the big A, B, C, and D, which is the parameter. So, since the target population will also come from the source population, the results from the A, B, C, and D can also be applied to the target population. This science of calculation of the statistic to estimate the parameter is called as inferential statistics, and the power to estimate and its power to estimate the parameter is referred to as external validity or generalizability of the results of the study. In cause and effect studies, for example, we were saying that in stroke patients, 42% would die if operated and only 7% would die if not operated. Therefore, there is a 6 times higher risk of dying if you opt for operation. So, this calculated research relative risk in the study population, which is statistic, will be generalizable to the source population and thus the target population, provided the sample size is sufficient. And for this we will have to calculate the sample size before we actually plan to conduct this randomized controlled trial, finding out mortality, dead and alive, in operated and unoperated patients. Now, since in this study comparing the operative and the conservative treatments of stroke patients, we, since we randomly allocated to the operative or the conservative group, this random allocation to the operative and conservative groups, if done over a sufficient sample size, would render the groups equal on all other explanations of the results. So treatment is one explanation, but there may be other explanations like age, like comorbidity. So all patient and disease characteristics linked to the dead or alive status of patients, which we call confounders, would be equally distributed in the two groups by random allocation, and therefore they will be unable to affect the dead alive status of the patient. Thus, the only explanation of the 42 upon 100 and 7 upon 100 dead which will remain will be the treatment type, operated or non-operated. So this characteristic of random allocation, rendering the compared groups equal on all other parameters except the treatment, and these parameters may be known or unknown, makes this random allocation as the most powerful method of comparing two treatment groups and is most useful in experimental comparative studies. So when we open the Excel file, and let us say on this side of the file we enlarge the magnification. On this side of the file, let us say there is the ID, any form of ID, let us say mobile numbers, and here you want to say selected or not selected for the study, not selected, and let us say here we put 1 and here we put is equal to sum, bracket open, this plus 1, which will give us 2. And we copy this through Control C and we copy it up to, let us say, 100. Control V. So these are the people who are either to be selected for the study or not selected for the study. So here what we do, we want to select, selected we'll say 1, and let us say we want to select 10, and we do not want to select the rest. So 10 out of 100 we want to select. So we say 0 here and see this dot here, copy this dot till the end, so that you get to 100, and so 10 we want to select. Now we generate a random number here. We say is equal to rand, bracket open, bracket close, star, and we want a number up to 100. Here is that number, and we copy this number, Control C, right up to the 100 and say Control V. So all these are numbers. And we can say Control V here also, and we can say Control V here also, so that all these are random numbers generated by the computer. Now we select the selected, not selected group and go up to the end say data sort, and we say sort by columns random. And when we say this, we find out that 23 is selected. Then we go on and say 48 is selected, 50 is selected, and all these have been selected randomly. So this is the method of random selection. Let us imagine that these are the blood pressure reductions seen in patients receiving treatment A and treatment B. Well, this is about treatment A, this is the central tendency, let us say the mean, and the values are distributed in descending order below it and above it. Same way, so this is called as dispersion, and this dispersion around the central tendency can be measured by a range, by a standard deviation, by a confidence interval, or by an interquartile range, means 25% are below and 25% are above. Now you see that if we have a higher sample size, this curve would become much more peaked as compared to this, and the area of intersection would decrease. So this is the effect of sample size. Greater the number in the study population, more the values near the central tendency, and therefore this will increase. The curve will become more peaked, and the area where you can belong to the two curves, intersection area, would become less. So you will be able to see the difference between mean reduction in treatment A and mean reduction in treatment B. So this is what you have to understand. Sample size gives you the power to see the two means as different. And this is the effect that we were talking about. You see, the curves have become more peaked, the intersection area has reduced, and now there is only a 5% area which is an overlap area between the two curves as compared to the total area under the two curves. So this is called as p-value, and a p-value less than 0.05 becomes significant, and it is the sample size, it is the peakedness of the curve which has made this p-value less than 0.05. So now we will tell you the sample size calculation. In the random selection out of the source population of 100, we had selected 10. So 10 is the sample size. How to get to that number, we'll tell you. So you see this epi here, and we switch this, take hold, click on this epi, and we get a stat calc here, which is the calculator. We put the stat calc here, and supposing we want to select for a cohort or a cross-sectional study, that means cause effect study, we say that A two-sided confidence interval, that means it can be better or worst, is let us say 95%. Power of the study to see the two results as different. Let us say that power is 80%. The ratio exposed to unexposed, that means operated to unoperated is 1, is 1. Percentage of outcome in the unexposed group. So we remember that there were 7 out of 100 that died. So we put here 7. And the risk ratio that we want to find out is, let us say, 2. Then we want 302 exposed and 302 unexposed, and a total sample size of 604. So this is the sample size calculation for a cohort or a cross-sectional study. And I have told you one method of doing it. You can also find out the sample size for population survey, unmatched case control studies, 2x2 table, live dead or binomial variable studies in populations. And so these are the various methods of sample size calculation that are available to you. Finally, let me tell you, to learn you must do. करत करत अभ्यास ते जड़मत होत सुजान, रसरी आवत जाते सिल पर परत निशान.